This is part 4 of the series, The Basics of Geometry. In the last part, we went over the distance formula, and I would like to begin this video with some practice problems. It's really important for these basic formulas that you do some practice before you move on so that you can incorporate these into long-term knowledge, and then you won't ever have to worry about this again. You'll know how to do the distance formula. It's going to be following us throughout the rest of the course, so it's an important one to get down. Now, I would recommend that you work each one of these problems separately, so pause the video before I work number 1, see if you can work it yourself, and then check your results. It's important that you do as much as you can do on your own before you watch me do it, so that it comes more from your brain instead of just copying what I'm doing here. So it's really important that you practice these if you want to get this down. Alright, so for number 1, we're looking for the length of AB. So let's go ahead and find the length of AB. For the first one, I'm going to go ahead and use both the distance formula proper, and then for the rest of them, I'm just going to use my own method, the SAS method, because it's a lot quicker. So for number 1, we know that distance equals square root of x2 minus x1 squared, the difference of the x's, plus the difference of the y's. So this gives us the x's. We could do 7 minus negative 4. 7 minus negative 4 squared plus difference of the y's, 8 minus 4. Now notice, since I started with 7 in point A and went to the negative 4, so x here, I have to go back to the y in A. If I started here and did this, and then went here and subtracted this from it, everything would be messed up. So wherever you start from, that's where you have to go back to. So it's this minus this, this minus this. Or you could have done negative 4 minus 7, and then 4 minus 8. Either way, it doesn't matter because we're squaring, so the signs inside here doesn't make any difference. But you have to be consistent. So 8 minus 4 squared. So this gives us 11 squared plus 8 minus 4 is 4 squared. So this gives us the square root of 121 plus 16, which is the square root of 137. That's the exact value, or approximately 11.7. Alright, and now I'll use my SAS method. So I'm going to take this point, 7, 8, and then this point, negative 4, 4. 7 minus negative 4, 11. 8 minus 4, 4. SAS square, add square root, and again we have the square root of 137. Alright, let's move on to number 2. So we'll go up here to do number 2. This time we're looking for BD. So it's negative 4, 4, and 3, negative 2. So negative 4, 4, and 3, negative 2. Negative 4 minus 3, negative 7. 4 minus negative 2 is 4 plus 2, 6. Square, add square root. This is the square root of 49 plus 36, which is square root of 85, which is approximately 9.2. All right, now for number 3. So in number 3, we're looking for the length of CV. So CV are these 2 points. So here we have -4, 4, and -5, -3. -4 minus -5 is -4 plus 5, which is 1. 4 minus -3 is 4 plus 3, which is 7. Square, add square root. So this is 1 plus 49, which is the square root of 50, which is approximately 7.1. Now, what I'm doing here is these values that we had for here, here, and here, for 1, 2, and 3, all these numbers are non-reducible values. If we had a number here that was simplifiable, that was reducible inside the radical, we would have to write this in simplest radical form. But because none of these numbers simplify effectively, then there's no point to doing that. When we get one that is reducible, I will go ahead and show you how to do that. But in this case, none of these work, so it doesn't really matter. We're just going to use the prime number here and its approximation. This is not a prime, but this radical is not simplifiable, so it doesn't really matter. All right, let's move on to number 4. And this is the length of DA. So we have this point and this point. So 7, 8, and 3, -2. 7 minus 3 is 4. 8 minus -2 is 8 plus 2, 10. And we do our SAS, square, add square root. So we have the square root of 16 plus 100, which is square root of 116. Now here we have an example where the radicand, that is the value that's under the radical sign, is reducible. And so what we have to do is do a process. You don't have to do it this way. There are other ways to do it, but I like to use what's known as prime factorization because there's very little chance of missing a factor. If you just try to factor this number out, you might miss some factor that you just don't see if you don't do it methodically. So that's why I like to use prime factorization. First prime number. A prime number is any number greater than 1 that is evenly divisible only by 1 and itself. So the first prime number is 2. And 2 goes into 116 58 times. So we're making a little factor tree here. And then we keep using the first prime number until we've exhausted it. And we know we're done when the value on the right here is a prime number. This is not a prime, so we know that 2 goes into 58. 2 goes into 58 29 times. 29 is a prime number, so this is our prime factor tree. In other words, the square root of 116, so the square root of 116 equals the square root of 2 times 2 times 29. Well, this is simply 2 times 2, which is 2 squared. Square root of 2 squared times 29. Now, a basic property of radicals is that if you have a product of two values, the radical of a product, that can be broken down as a product of radicals. Hopefully you went over this in algebra, but this is a little refresher. The square root of anything squared, the square root of any quantity squared, is that original quantity. And it's easy to figure this out. If you looked at 2 squared is 4. The square root of 4 is 2. So the square root always cancels out the square, and you're left with the value inside. So because the square root of 2 squared is just 2, this result comes out to 2 square roots of 29. This is the simplest radical form for this answer. And we can find the result, the approximated result, by simply plugging this into your calculator. But you may be asked, in fact, you will probably be asked, what is the simplest radical form of the exact value of this distance, of the length of dA, and this would be the answer. Just for reference, the approximation, a little hard to write down here, is approximately 10.8 to 1 decimal place. Okay, then for number 5, we're looking for the length of AC. So that's 7, 8, and negative 5, negative 3. So 7, 8, negative 5, negative 3. 7 minus negative 5 is 12. 8 minus negative 3, 11. SAS, square add square root, 144 plus 121, square root, that's the square root of 265. And this number is irreducible, so that's approximately 16.3. Alright, well that was just some basic practice. I would recommend that you go ahead and make up some problems, and if you don't have this down yet, if this is not pretty automatic for you, practice a couple more times, and also practice some of this prime factor tree work, and see if you can't get that done as well, just so that you don't have to worry about the simple formulas and you can focus more on the more complex topics as we move on. Alright, let's move on to the next piece. We've been talking about the length of line segments. So let's consider segment AB and segment CD. If we find the length of these two segments, either by the ruler postulate or by the distance formula, if we find that the lengths of these two segments are equal, then we would say that segment AB is congruent to segment CD. Again, here you can see that this segment, AB, is 6.2 and AC is 6.2. These two segments have the same length, therefore those two segments are said to be congruent. The definition of congruent segments is, two line segments are congruent if and only if their lengths are equal. Now this statement can be broken up into two pieces. It means two line segments are congruent if their lengths are equal, and if two line segments have equal lengths, then they are congruent. So we're going to look at statements like this in the next chapter. Now graphically, you would show this by these little hash marks here. There could be 1, 2, 3. You only have to match up the number of hash marks. Here, these two segments have 2. So this is congruent to this, and this is congruent to this. This is not necessarily congruent to this. In mathematical statements, you would say segment AB is congruent to segment CD. This equal sign with a tilde across the top is congruent symbol. So because AB is congruent to CD, the length of AB is equal to the length of CD. Now it would be inappropriate to say line segment AB is equal to line segment CD. If we swap these symbols, these statements would be wrong. Just as it would be inappropriate to say the length of AB is congruent to the length of CD. You can't do that. It's segment congruent to segment, length of equals length of. Length of equals length of, segment congruent to segment. So that's the idea of line segment congruence, and you're going to be using this throughout the course. It's a fairly simple concept, but it's one that you have to have down at this point. Alright, let's move on to the next topic, and we'll do that in the next video.